Hello and welcome to Conceptual Physics at Delaware Tech, Chapter 3, Linear Motion. So in this unit, we're going to cover how motion is relative to who's observing that motion. We'll talk about speed in terms of average speed versus instantaneous speed. We'll talk about the use of the term speed versus velocity, and I've already touched on this a couple times. So it shouldn't be that unusual to you. And we'll talk about acceleration and the definition of acceleration, as well as the mathematical definition of acceleration. And then we'll cover free fall and how fast free fall means. So this is falling due to the acceleration due to gravity. And we'll talk about how your speed increases as you're falling further, or an object is falling further, and how much distance you cover as you're dropping. And then we'll talk a little bit about velocity vectors, just like we've already talked about adding and subtracting vectors in the past. So motion is always relative to something else, who's ever observing the motion, because whoever's observing might be in motion as well. And so motion of watching an object may appear differently to different observers. So if you're traveling in a spaceship at a constant speed in a straight line, in other words, a constant velocity, with no stars or planets in sight, in other words, you have no reference points at all, can you really tell if you're moving? You may have noticed this if you're riding in a train in the dark. After a while, you might not even know that you're moving, if it's a steady train, if it's a smooth track. If you're standing still, but the Earth is rotating and it's moving around the sun at the same time, and the sun is moving around the galaxy, and the galaxy is moving within the cluster of galaxies, are you still moving? Well, you are, but it depends on your frame of reference. It depends on how you're looking at it. And things you're looking at, they're relative to you, how they appear in their movement. So if you walk on a street relative to the Earth, but the Earth is moving relative to the sun, are you really moving, right? That is your motion relative to the sun is going to be different than relative to the Earth. And for the most part in this course, we're going to talk about things moving, things dropping, cars driving. It's going to be relative to the surface of the Earth. So we're not going to worry about the Earth rotating. We're not going to worry about the Earth flying around the sun at 30 kilometers per second. We're not going to worry about the sun moving around the galaxy, etc. So it'll be just like it appears, just normal, like if you see a car moving, and it's moving relative to you standing outside of the car, unless we say otherwise. All right, so speed and velocity. Velocity, remember, is a vector term, so it includes direction, but it's essentially the amount of distance covered per unit time of travel. So what it means is it's distance that you've traveled divided by how much time it took you to travel that distance. So because it's a term that's created by taking distance and dividing by time, the units are all based on distance dividing by time. So in metric and SI units, the units are typically meters per second. Meters is our distant unit, seconds is our time unit. But we have other variations of this: kilometers per hour, centimeters per minute, millimeters per year. If you're talking about the tiny movement of, say, continents, you might use something like that. We have imperial units. This is what people typically call the English system. The imperial units have things like miles and yards and feet in them. So you might have miles per hour, which people write MPH. I try to avoid MPH because I want you to think of it as distance divided by time. So it's miles divided by hours. And in these slides, I try to show the units that way so that you can see what units are in the numerator and what units are in the denominator, so it's easier to cancel them. That doesn't always appear that way in the exams and in the problem sets, but I try to do my best to keep them that way in the unit presentations. So speed is distance divided by time. For example, if a girl runs 4 meters, that's the distance she covers, in 2 seconds, her speed is 4 meters divided by 2 seconds, or 2 meters per second. So when you're dividing or multiplying these things that have units, these properties that have units, you have to multiply and divide the numbers and you have to multiply and divide the units in order to get the correct unit. So some meter value divided by some second value will give you meters per second, meters divided by seconds. And we would say this as 2 meters per second. Per means divided by. Okay, so before Galileo, people didn't really have a quantitative concept of speed or velocity. If something was moving, they would say it's moving slow or moving fast. Of course, it was in Italian because that's where Galileo was from, Italy. But they didn't quantitate these speeds. So he's credited with the concept of defining speed as distance divided by the time of travel. So the average speed, we're going to talk about different versions of speed and different versions of velocity. Average speed is the total distance covered divided by your total time interval. So, and why we say that is we want to distinguish it from instantaneous speeds. Instantaneous speed means the speed right this second, or that second, or this moment in time, that instant in time. That's why it's called instantaneous. So average speed covers a whole trip. And during that trip, you might have slowed down, you might have sped up, but the average speed is that middle speed that the whole trip behaved as. In other words, if I went up and down, and sometimes I was going 0 miles per hour, and sometimes I was going 100 miles per hour, and the average turned out to be 60 miles per hour, well, I know if I drove 1 hour, even though I changed speed constantly, but I averaged 60 miles per hour for 1 hour, I traveled 60 miles. No matter how my speed changed in the middle, as long as I know the average speed, I can figure out my total distance from my total time. So for example, if you drive a total of 200 kilometers in a total of 2 hours, remember it's distance, total distance divided by total time, 200 kilometers divided by 2 hours is 100, that's the number when you divide the number, and then the units are kilometers divided by hour, so it's 100 kilometers per hour. 100 kilometers per hour is about 62 miles per hour, by the way. So the average speed of driving 30 kilometers in 1 hour, 30 kilometers per 1 hour, is the same as the average speed of driving 30 kilometers in a half an hour, 30 kilometers in 2 hours, 60 kilometers in a half an hour, 60 kilometers in 2 hours. Well, if we look at the first one, 30 kilometers in 1/2 hour can't be the same speed as 30 kilometers in 1 hour. We're taking half the time. In B, we're taking double the time, so that to cover the same distance, so that can't be right. C, we've got double the time, double the distance and half the time, and does that make sense? And then D, we have double the distance and double the time. Well, it's of course D. If we work out the average speed of 30 kilometers in 1 hour, it's 30 kilometers per hour, per 1 hour, right? And if we work out each of the individual ones, we see that 30 kilometers divided by a half an hour is 0.5 hours. And sometimes it's worth turning these into decimals to do the math easier. 30 divided by 0.5 is 60 kilometers per hour. 30 divided by 2 hours is 15 kilometers per hour. The third one, 60 kilometers, we've doubled the time, doubled the distance, but halved the time. That's 4 times the velocity. That's 120 kilometers per hour. It's the last one where we've doubled both the numerator and the denominator. When you double both of them, the doublings cancel, and you end up with the same value, 30 kilometers per hour for both of them. Think of it this way. If you were driving 30 kilometers in an hour, and you kept that average speed for the next hour, that would be another 30 kilometers for that hour. So you went 30 kilometers in 1 hour, and you went 30 kilometers in the other hour. That's 60 kilometers in 2 hours. That's the same thing. Your average speed never changed. So it makes intuitive sense as well as mathematical sense. So instantaneous speed is a speed at any instant in time. So, for example, when you ride in a car, you may speed up and slow down to any instantaneous speed that's going to be different, that may very well be different from your average speed. The only time it's not going to be different from your average speed is if you were somehow able to control your speed with, like, say, cruise control, and you kept the exact same speed the entire trip, And yeah, your average speed will be the same as your maximum speed. It'll also be the same as your minimum speed. But in general, your instantaneous speed, which is given by what's on the speedometer, it's pretty much always going to be greater, or at least greater than or equal to your average speed. Your instantaneous will always be greater than your average, unless you stay the exact same speed all along and then they're the same number. So speed and velocity, to a physicist, they're just not the same thing. Velocity includes a direction. It's the instantaneous speed, how fast you're going, plus the direction. Am I going north? Am I going east? Am I going that way? Am I going left? Am I going right? Any direction. Am I going 45 degrees from the in an angle from some other direction? That's a direction. So once you add a direction, it's a vector, and then we call it technically velocity. You will hear me say speed and velocity almost interchangeably throughout the semester, and that is usually because when we're talking about velocity, we're frequently not concerned with the direction, so speed is an okay word to use. So don't get too hung up on it, but there is a technical difference that you should be aware of. All right, so velocity is a vector quantity. It has a magnitude, 8 meters per second, 60 miles per hour, but it has a direction, due north, left, whatever. Okay, so if it's just a magnitude, that's a scalar. The technical word would be speed in this case, and if it has a direction, well, then it's a vector. So that's how we distinguish between vectors and scalars. In some cases, this will be very important. So here, I know I just told you most of the time it's not, but there's some cases, and this is one of those cases. So constant speed is steady speed. You're not changing how fast you're moving. You're neither slowing down or speeding up. So I've got a linear speed shown on the top ball sliding down this line, and I've got a rotational speed, an angular speed of a ball going around in a circle. And they're both moving at constant speed. They're not changing their rate of motion. The distance they're covering per time is the same, whether I'm going straight or in a circle. However, if we're talking about velocity, the top one still has constant velocity. We're not talking about restarting here. We're just talking about the movement down the line here. It's constant speed, constant velocity, because it's not changing direction either. Whereas in the circular motion, the direction is changing every instant in time if you're going in a true circle. Every instant in time, the direction's changing, and therefore your velocity is never constant when you're moving in a constant speed in a circle. So these need to be distinguished. The second you make a turn in any way, shape, or form, a little bend, a tiny curve, a big curve, a sharp right-hand curve, your velocity is no longer constant. Your speed might be, but your velocity is not. So no acceleration means no increase in speed, no decrease in speed, and no turns. And when that is the case, if you're still moving, that's dynamic equilibrium. If you're not moving at all, and your velocity is constant, but it's constantly zero, that's static equilibrium. So they're both constant velocity, but static equilibrium, that constant velocity happens to be zero. So motion, we're going to, as I said before, is going to be relative to the Earth unless we say otherwise. All right. So acceleration is a term we need to understand here. And this was formulated by Galileo, just like speed and velocity were, and based on the inclined plane, the ramp experiments we talked about before. Things speed up when they roll downhill, things slow down when you try to roll them uphill, and when they're on a flat surface that doesn't have much friction or air resistance, they'll keep going at a constant speed in whatever direction they were going. So the rate at which velocity changes over time, that is considered acceleration. So it's technically the change in velocity over the change in time. And we define that this way mathematically. The change in velocity over the time interval, that's another way of saying the change in time. But usually the change in time is just how much time. So we just simply say t. When we want to say change in something, we use the Greek letter delta, the capital letter delta that looks like a triangle, and that means the change in whatever is following that letter. So let's let's talk about acceleration, what it means in physics. As I said before, it's a change in speed or a change in direction or both. A car making a turn at a constant speed. The reason why we know there's an acceleration, a change in velocity, think about being in a car. If you're driving in a car and your car speeds up, you get thrown back. Why? Because your body has inertia. It's not used to that speed. It wasn't moving at that faster speed. So what's really going on is not that you're thrown back, it's that the car is thrown forward by the accelerator, and your body just hasn't responded quickly enough to it. So we look at it from our own perspective, but from an outsider's view, it's the car that's accelerating into our back when it accelerates. And same thing when we're slowing down. When we hit the brakes, we move forward. It's not that we're moving forward. We were always moving forward at a certain speed, and the car suddenly slowed down into us. And that becomes more evident when you're in a car accident for not so pretty reasons. But also when you're making a turn, let's say you're making a left turn or you're going around in a circle, which way does your body feel like it's going in the car? It always feels like it's going opposite the turn. But it's not really that it's opposite the turn. Your body thinks it's going in a straight line. It's moving in a straight line, and your car is bending this way. If your car is turning this way, your body is already going this way. So in the car, you feel like you're being thrown to the right, when in fact you're really just continuing moving forward, and the car is pushed against you to the left. So it's really kind of an illusion, and using physics really makes you realize that much of what you experience in everyday life is not always the way you think it's happening. So the car is constantly changing direction if you're moving around in a circle to the left, and you always feel like you're being thrown to the right, but in fact you're always trying to move straight as the car is constantly changing direction. So to a physicist, as I mentioned in the last unit, a physicist thinks the car has three accelerators: the actual gas, the accelerator, the brake that slows you down, and the steering wheel that changes your direction. All right, so acceleration is the change in velocity, the delta V. Delta V means change in velocity. And anytime you see a delta anything, delta position, delta velocity, delta force, delta change in weight, your change in weight, your change in velocity, change in temperature, delta something. It is always, always, always the final version of that number minus the initial version of that number. So you'll see I have velocity sub f. That's the final velocity, also called the instantaneous velocity at a certain moment in time, minus the initial velocity, v sub I. And sometimes people will write v sub f as just v. Sometimes they'll write it as v sub instantaneous, though I don't use that. It's too long. They'll write the initial velocity as v sub I for initial, or v sub 0 for the velocity at 0 time. So please try to get used to that. People interchange those all the time. You'll see different ones in different books, in different texts, in different documents throughout this course. Time is technically a change in time, but because the initial time is always 0, the change in time is just how much time. So we just write t, simply t. So this is our definition. Acceleration A is change in velocity divided by time. And if you rearrange this formula and move time to the other side, you see acceleration times time equals the change in velocity, and this will come up soon. So don't be afraid when you see this other version of the equation. It's the same thing. It's just the definition of acceleration rearranged. All right, so let's use this to figure out the units. Since acceleration is a change in velocity, remember velocity is distance per time, but it's change in velocity divided by time. So it's distance divided by time again. And as a result, your units are in distance per time squared units, or distance per time units, sometimes two different times. So the most common one we use is meters per second squared, which is really meters per second, that's our velocity, per second, a second per second. I know that's confusing. And what that means is your speed, let's say you had an acceleration, in this case, you have your initial speed is 40 kilometers per hour. So that's where you're going before you start doing anything. And 5 seconds later, you increase that speed over the next 5 seconds, you increase it to 45 kilometers per hour. So you've increased the speed by 5 kilometers per hour. Your final minus your initial, it's always final minus initial, is 5 kilometers per hour. That's your change in velocity. You divide that by how much time it took to change that velocity, 5 seconds. So 45 kilometers per hour minus 40 kilometers per hour, your delta V, divided by your change in time, which is 5 seconds minus 0. So we just write 5 seconds. Over 5 seconds. Well, that's 5 kilometers per hour per 5 seconds. That works out to 1 when you divide the numbers, and when you divide the units, it's kilometers per hour per second. And you can group the hours and seconds both in the denominator, but that would be awkward looking, so we would typically write it as 1 kilometer per hour per second. And it's a positive number because we are increasing our speed, our velocity, so it's a positive value. You can have negative accelerations if you're slowing down. Okay, so here's your question. An automobile is accelerating when it is A, slowing down to a stop, B, rounding a curve to a steady speed, both or neither. Well, we've learned that changing your speed and changing your direction are both considered acceleration to a physicist. You increase your speed or decrease your speed, that's acceleration. Decreasing the speed, we would call negative acceleration. In everyday English, you call it deceleration or braking, but to a physicist, they just put a positive and negative number, a positive and negative sign in front of it, and call everything acceleration. But it also includes direction, so any change in direction, even if the speed is the same, is considered acceleration to a physicist. All right, acceleration and velocity are actually A, the same, B, rates, but for different quantities, C, the same when the direction is not a factor, D, the same when an object is freely falling. Well, think about it. That's B. They're both rates. Remember, velocity is the rate of distance per time. It's the change in distance, a change in distance or change in position per time. So it's your final distance, your final position minus your initial position, or just the total distance if you have that, 5 miles, divided by time. So that's a rate of change of your position or distance. Whereas acceleration is your rate of change of the velocity, of the speed. Okay, so velocity is the change in your position with time. Acceleration is the change in your speed with time, or your velocity with time. So they're different, they're measuring different things. So Galileo looked at acceleration, and he used these inclined planes, and I've got boxes sitting on the tops of a bunch of different ramps. And you'll notice the steeper the ramp gave greater acceleration coming down. And I can't really graphically show you that they are actually all getting faster as they move down, but that's what really would be happening here. Okay, so when the incline is vertical, that's the same as just dropping the object without having any ramp at all. So that's free fall as long as we're going to ignore any drag. Drag is the technical term for air resistance or air friction as some objects falling through the air. And we'll talk about that in another unit, in the unit on gravity. Okay, so all objects will fall with the same acceleration when we ignore air resistance. Air resistance becomes very complicated. We'll just talk about air resistance. I'll say, hey, air resistance is this much force, and that's all you have to worry about. The calculation can get a little hairy. All right, so all objects, we're going to assume all objects, all sizes are going to drop. All densities are going to drop with the same acceleration, the same distance per time. All right. So what's interesting is the effect of air resistance when it is important, and that's important when you have things like feathers or cloth falling. Yes, they're going to be slowed down by air resistance, as opposed to a chunk of metal. When you drop it, there's not that much air resistance. It'll come down pretty much with the acceleration due to gravity. Galileo found when he used two balls and dropped them from the Leaning Tower of Pisa, they dropped at pretty much the same rate, but they were both balls. They were the same shape. They were the same size. They just had different densities, so they had different weights. So the air resistance was pretty close to the same as they fell. So it wasn't important in his calculations. But here's a little video that I've embedded in here, and I'm just going to play like 30 seconds of it near the end. And this is a feather and a cube of metal. And what this guy did was he put them in a box, and he let the two drop from the top of the box when there was air in there, and then he pumped out the air. So it was a vacuum, no air resistance. And then he let the feather and the metal drop in that one. So I'm going to show you two side by side. They're both in slow motion. On the left side of this video is the vacuum. So there shouldn't be any air resistance. And if you think about what should happen here, normally a feather is going to take a lot longer to fall. And that is because of the air resistance, not because gravity affects a lighter thing differently than a heavier thing. It affects them with the same acceleration. They're different forces, and we'll talk about that later, but they have the exact same acceleration. They speed up the same way as they're falling if there's no air. So in this video, on the left side, there's no air with a feather and a chunk of metal, and on the right side, there is air, and it's in slow motion. Let's take a look. You can see on the left, the feather and the metal dropped at exactly the same acceleration. They got faster and faster together.
In normal speed, so you can appreciate how fast the feather.
So now you're going to see what this looks like in a vacuum with a feather and the chunk of metal dropping in a box with no air at all, no resistance. And this is what a feather would do if it was just falling due to the acceleration from gravity.
Feather actually falls. So here's feather in a vacuum, normal speed. 3, 2, 1.
It's kind of startling to watch a feather drop to the ground that fast, but that's what happens. No air resistance. Feel free to watch the whole video. All right. So falling under the influence of only gravity, in other words, no air resistance, no drag, that's what it's called, no air friction, that's what it is. That's the acceleration due to gravity. We use the letter A for that value of acceleration. And if that acceleration is the acceleration from gravity, in other words, we're talking about falling as opposed to going in a car and accelerating, we call that acceleration G for gravity. So G is just a one form of A, of acceleration. So the acceleration due to gravity on Earth is about 10 meters per second squared. In other words, if you start with no velocity and you drop an object, 1 second later, it will have increased 10 seconds for every second it falls. 10 meters per second, 10 meters per second per second. So the first second, it'll get up to 10 meters per second. It is increased by 10 meters per second in the first second. It'll increase another 10 meters per second in the second second. So it's getting faster, it's dropping further. So by 2 seconds, it will be at 20 meters per second. It's doubled its speed. At 3 seconds, it'll be at 30 meters per second. At 4 seconds, it'll be at 40 meters per second. So the velocity going down will be faster and faster by adding 10 meters per second every second it drops. So if you know what a speed is at a certain time, you know what it'll be a second later. It's 10 more than that in meters per second. Or if you want to go backwards and say, hey, I know that at this time it was 78 meters per second. Well, 1 second ago it was 68 meters per second, 58 meters per second in the second before that. And 10 is a rough number. It's actually closer to 9.8, but for this course, most of the time just use 10. It'll make the calculations easy and you'll get numbers that are close enough. All right, so that's what this is saying. It's 9.8. The average acceleration for Earth is 9.80665. Don't ever worry about that. This equates to about 32 feet per second squared if you're using the imperial system. In other words, at 0 time, it's not moving at all. You drop it. In 1 second, it's 32 feet per second. After 2 seconds, it's double that, 64 feet per second. At 3 seconds, it's 96 feet per second. So it's not only moving faster, it's covering more distance as it goes faster. So those are the more precise values in case you're interested. You don't have to use them. That's why I didn't even highlight them. Okay. So remember I told you about that definition of acceleration. It's A is equal to delta t over, A equals delta v over t. If you rearrange that and solve for delta v, the change in velocity, your change in speed as it's falling, that's equal to A times t. But if you're falling, A is g, the acceleration due to gravity. So this is really delta v equals gt if you're falling. I didn't put gt in here because if you're traveling in a car and accelerating, you can just use whatever A is in the problem. Delta velocity, the change in velocity, is always the final minus the initial. Remember, it's always final minus initial for any delta anything. But if you're just dropping something, your initial velocity is 0. So your change in velocity, Vf minus your initial velocity, is your final velocity minus 0 velocity. So that's the same thing as saying that your change in velocity here on the right, you see in the blue highlighted, the change in velocity is the same as your instantaneous velocity, your final velocity, and that's equal to A times t, as long as you started at 0 velocity, as long as you're just dropping something or letting something start from rest. We're not going to get into more complicated calculations in this course. So your final velocity of falling is gravity times time. So at 0 seconds, you're at 0 velocity. Gravity times 0 time is 0. At 1 second, it's 10 meters per second. So this is the calculation that matches the intuitive thing I told you before of adding 10 meters per second for every second you're falling. After 2 seconds, 20 meters per second. 3 seconds, 30 meters per second. And if you look in the little graphic on the right here, you see the speed is changing on that little speedometer, but what you also see is the distance that's covered is much greater in subsequent seconds. Now, it's not that it jumps in speed or that it jumps in distance. This is all a gradual process, but it works out to these numbers when you calculate it. So it's gradually getting faster, and it's gradually covering more distance as it falls. So at a particular instant in time, so an instantaneous velocity, that final velocity, a free falling object has a speed of 30 meters per second. 1 second later, its speed will be the same, 30 meters per second, 35 meters per second, more than 35 but less than 60 meters per second, or 60 meters per second. Well, I think we just said that after 1 second you add another 10 meters per second. So it'll be about, it'll be about, there we go, about 40 meters per second. Well, I'm jumping around here, sorry about that. It'll be about 40 meters per second. It's slightly less because it's not really 10, it's 9.8, but don't worry about that. So the answer is C. All right, so we've already done these calculations. These are our instantaneous speeds at the different times of dropping an object. Any object, as long as air resistance is not an issue. It could be a marble, it could be a bowling ball, be a tractor trailer being dropped from some skyscraper. They will all have the same change in velocity if we neglect air resistance. But what about the average speed? Not the instantaneous speed, which is the final speed at any one moment. The average speed. Well, the average speed is the average of two speeds. The initial speed, which we have already said is 0, and the final instantaneous speed. Well, when you average 0 with any number, you're adding them together and dividing by 2. That's the same thing as just dividing them by 2. So as long as you're starting at 0 initial velocity, your average speed for the whole drop is just half of the speed of the fastest speed. So you went from 0 to something fast, the average speed is halfway between those. It's not half in distance, it's half the number. So I started at 0 meters per second and I ended at 100 meters per second. The average speed along the way was 50 meters per second. So in this case, because our initial is 0, our average speed for the whole trip is just half of whatever we got before. A final speed of 40 meters per second on the bottom here at 4 seconds means that during that whole 4 seconds, you averaged 20 meters per second. You were 20 meters per second at an earlier time at 2 seconds, but you averaged for the whole trip 20 meters per second. And that's important if you want to calculate distances, because if you know the average speed for the whole trip and you know how long the whole trip is, the average speed times the time is just equal to your distance. So all right, so the average speed is just half of the instantaneous speed, the final instantaneous speed, and that's represented here. You don't have to worry too much about the calculations, but it's just one half of the final speed. The final speed is just a times t, or g times t if it's falling. So your average speed is 1/2 at, or 1/2 gt. So the distance that you fell for that whole period of time is the average speed, 1/2 gt, times another t. So it just works out to 1/2 gt squared, or 1/2 at squared, depending on what letter you want to use for that context. A is all kinds of acceleration. G is the acceleration from falling, from gravity. Okay, they mean the same units. They mean the same process. They just are in different contexts. A is any kind of acceleration. So we have this formula: distance falling, or distance covered from any acceleration, even if it's horizontal or vertical, is 1/2 times the acceleration times time squared. And you're going to square both the number of seconds as well as the second unit. And you can do that by also multiplying it 1/2 times acceleration times time, and then multiply it by time again, whichever way you're more comfortable with. So at 0 time, the calculation's easy. It's 1/2 times 10 meters per second squared. That's the gravity acceleration, times 0 time times 0 seconds times 0 seconds. So it's 0 meters. That makes sense. You haven't started falling yet. After 1 second, it's 1/2 times 10 times 1, or 1 squared. That's 5 meters. So after 1 second, your final speed at 1 second is 10 meters per second. At 1 second, you've fallen, you're getting faster, you're at 10 meters per second. That's your velocity. Your average speed is half of that, 5 meters per second, and you've fallen for 1 second. 5 meters per second times 1 second is 5 meters. But you don't have to think this all out. Just use 1/2 gt squared. And these formulas are all in your formula sheet, so you don't need to memorize them. Just become familiar with them. At 2 seconds, it's 1/2 times 10 times 2 squared, or 4. So 1/2 times 10 is 5. It's always going to be 5. 1/2 times 10, 5, times 2 squared is 4. 5 times 5 times 4 is 20 meters. At 3 seconds, 3 seconds squared is 9 seconds squared, times 5, 45 meters. And you can keep doing this for any time period. And you'll get roughly the distance you fell if you're falling with gravity. If you're going horizontally and accelerating, you have to use a different acceleration. You can't use g, but it's the same formula. So what's the distance covered by a freely falling object? That means no air resistance. Starting from rest, that means 0 initial velocity, after 4 seconds. So you're falling for 4 seconds. 1/2 gt squared, where t is 4 seconds. Give you a second to figure it out. It's going to be 80. Remember, it's 1/2 times acceleration times time, or time squared. So 1/2 times 10 times 4 squared. 4 squared is 16. Times 10 is 160. Half of that is 80 meters. So this is a little reminder of your vectors. I know I keep reminding you your vectors, but it's a good idea. So let's consider a situation where you have a plane that's flying north in this diagram. We'll say up is north here, and we'll say to the right is east. And this plane is flying north at 80 kilometers per hour, and there's a crosswind blowing towards the east at 60 kilometers per hour. So the crosswind is going to push the plane as it's trying to fly this way. It's going to be pushed this way, so you're going to end up with some diagonal value. Well, if you calculate what that is, we can do that with the parallelogram rule, which ends up creating a rectangle because they're perpendicular to one another, so you make a rectangle. And once you have a rectangle, you can use Pythagorean theorem to look at the diagonal of this rectangle. So 60 squared plus 80 squared Take the square root of that sum and you get 100. In other words, 60 squared plus 80 squared is 100 squared. So you know your diagonal has a velocity of 60 kilometers per hour, and it's at some angle relative to eastern direction. We're not going to worry about what that angle is. You can calculate it with trigonometry, but that's beyond the scope of this course. If you were to use trigonometry, it works out to 53.13 degrees, but don't worry about that. There will be some times where you'll know angles just because they're obvious, and that actually comes up in the rest of this question. But for that question, you have to use trig to solve the angle. But let's consider a different version of the same problem. And in the second version, the plane is still flying north at 80 kilometers per hour. But now the crosswind is 80, not 60. So it's 80 north and 80 east. Well, what does that mean as far as the new diagonal? Well, I'm telling you, if you use Pythagorean theorem, you'll find that the length, the magnitude of that new velocity is 113 kilometers per hour. So we've given you that. The question is, what's the angle? And I just finished telling you, we're not going to calculate angles, but I want you to think logically about this. If one side of your rectangle is 80 and the other side of your rectangle is 80, that's not a rectangle. Well, it's a rectangle, but it's a special kind of rectangle. 80 by 80 would be a square. So our parallelogram, which became a rectangle, the rectangle now became a square. When they're perpendicular and they're the same, it's now a square. The diagonal, as I said, was calculated as 113, but we know that half of a right angle is 90 degrees. If it's halfway between, it's 45 degrees. So our answer is 45 degrees. And with this, we'll end the unit here.